live. Wow. All in one go. Introduce myself. I'm Rolf Hart. I am assistant professor at Delft University of Technology. I'd like to thank Simon and the Royal Meteorological Society for inviting me here. My career hinges kind of on two legs. One of them is hydrological forecasting globally, doing flood forecasts based on the weather forecast, running it on supercomputers. That's not usually what I'm known for because it's less media savvy, I guess, than the other work I do, which is low-cost design of sensors in hydrology. And so I'm not a meteorologist by training. I'm even not a hydrologist by training. I did physics in Delft. Specialty in room acoustics, by the way. This is pretty good. And as academic rooms go. But then I branched out into environmental sensing for water management and hydrology. One thing I'm coming back to at some point, water management is normally part of environmental sciences or that corner of academia, not in the Netherlands. In the Netherlands, water management, for obvious historical reasons, is civil engineering. And that will make sense in a few moments. One of the projects we did recently, just to show you low-cost sensing, is colleagues of mine, and oh, this is really visible, nice. Colleagues of mine wanted to know the mixing processes between the Irrawaddy River and the Chindwin River, one of its tributaries. This is the Irrawaddy, this is the Chindwin. This is low flow season. In high flow season you wouldn't even see this bank, and the nice thing about this picture and this bank is that you can, it's a perfect 90 degrees. The location, by the way, if you look this up on Google Maps, it's different every year because of sedimentation processes. This is also why we want to study that. The Chindwin has way more sediment. Normally doing these kind of dispersion measurements involves high-end GPS trackers, high-end samplers. Those are expensive. So just showing you what it looks like. The top-down view, yeah. So this is the Chindwin, this is the Irrawaddy. We want to know how long it takes before they completely mix. And the way we did that is by releasing about 500 coconuts with balloons tied to them, and have Dutch bike lights in the balloons, and then have student teams on bridges count them. That was the low-end part. The high-end part, relatively high, were these devices that I built. These are floats made from locally found materials, but the interesting thing is over here, little solar panel, and this box contains a particle electron, which is a Arduino-like board, but it's made to communicate. It has a GSM modem in it, and it has a GPS receiver in it. So every 15 minutes, every minute it wakes up, it knows its own GPS location. Every 15 minutes it calls in and uploads that location to us, so we could track how they flow down the river, and then by the distribution of multiple of these sensors we get an estimate of the dispersion coefficient of the river. So that's one thing I do with building low-cost sensors. This setup, this thing is under 100, including its data subscription. And this is, oh, now I forgot what the local currency was, but less than €2 if you do it in my currency, sorry, not yours. So that's one thing I do. One of the other things I do is I take what I know about making low-cost sensors and apply it in my teaching. I teach a course called Measuring Water every year to civil engineering students, the end of bachelor's. And they get the assignment, here's a little piece of electronics, make any sensor that measures something with water, put it online. If you do that within 3 weeks, and I can see like low, middle, high values coming online, you're good. And they can pick any process that relates to water. So these are a few students that made, one of them measured the amount of water that comes off a roof drain. So they made kind of a U-bend in it and then holes, and so the more holes contribute, the higher the flow coming in is, and they could sense that very well. These students use traffic pylons to create a venturi tube, So that creates a pressure difference as to what, this is one of our flumes in our lab. So it creates a pressure difference over it. You see some PVC over here, and there's another one hidden behind his hand. So the pressure, so there's styrofoam in there. So the styrofoam pressure pushes against some pressure sensors, and the difference between those two pressure sensors gives you a very good approximation of the discharge through this tube. That's the kind of teaching I do, low-cost sensing teaching. So my course starts November 13 and ends December 4th. So you're gonna at least 20 things for your Switch campaign right there. I'm just gonna change the assignment into give me a report into submit something to Switch. So, and they'll already be built.
Yeah, don't forget the flyers.
Yeah, no, I'll take a few flyers home. And then finally, a project I've been working on for 7 years now, that does relate more to your specialty in meteorology, is the TAMO project, Trans-African Hydrometeorological Observatory. Our group in Delft has done a lot of work in Africa, and we realized that we're losing ground data. If you just count the number of stations, it's been going down since 1900. And to make good predictions on the ground, we need those stations. I mean, satellite is helping, but it's not enough. Actually, in the Netherlands, if you produce a PhD thesis, you get to have, what's it called in English? Got to make some statements that are defendable. It's kind of a very old tradition. And one of mine was that with the advent of satellite data for environmental sensing, we actually need to increase instead of decrease the amount of ground measurements we're doing. Because otherwise the value we get from that satellite data is not worth it. Even if you do the calculation, because every satellite measurement would also be less than a penny, I guess. But still, it will only be really worth it for society if we have good validation data on the ground. So the TAMO project set out to design and implement 20,000 weather stations in sub-Saharan Africa, which would mean that if we all put that in GCOS, it would change from something like that. These are the actual stations. These are not the stations that are reporting. You have to take away about half of the dots in here if you want to have the nicely operational ones providing good data. But if we manage to do what we set out to do with TAMO, you would have something like this. And I think that is about the resolution we need to do good agricultural predictions, good flood predictions anywhere, especially in Africa. However, with current technology, that doesn't work. Current weather station, if you leave that for a few seasons, usually what we do, we put those in, we leave them out there, we come back, we find them, okay, this is exaggerated because there was some kind of fire, but most weather stations designed by people from Switzerland are not meant to survive in Africa. Also, people in Africa are not able to afford things that were devised by people that earn their money in Swiss francs. So there's a big problem there. We set out to tell the community of sensor designers and the community of commercial weather station manufacturers, there is a market for different things than you're doing right now. To be exactly, make it no moving objects, make sure that they're replaceable for a few $100s, and the total cost should be less than 1,000. Because if we want to have 20,000 of these things, you're talking millions. If you want to have 20,000 of these things at current cost, you're talking billions. Nobody's going to invest billions in a sensor network. And then the way we tried to convince them was by showing what could be done. One of our first prototypes was that we went to the rain gauge. This is the first prototype of our acoustic rain gauge. Basically a piezo disc glued to a photo frame, and then we use that to show to everyone for €5 you can make this. Please include that into your weather stations. And then they said, well, that's going to be hard and stuff, you do it yourself, so we did. We try to make a company out of that, and we're now almost in the phase where we can have these sold commercially. So acoustic disdrometers that measure every drop just by the impact of it. And because we went that road, companies started moving, luckily. So I think about 1.5 years ago, the meter company that used to be Decagon, but they fused with a German company, they're now calling themselves Meter. You try to Google that. I think it's not a smart decision, but someone in marketing made a lot of money on it. So the Meter company now made a, is there someone from Meter here that I'm now, no, okay. No, and they're really good people. I mean, we work with them. I'll come to that in my next to last slide. We work with them a lot. It's just that I think the name, I would have chosen something else. They made a weather station that adheres to the design specifics that we said if we have that, it'd be useful for Tammo. So it's this weather station, and we now have, I think, 250 installed over 10 African countries. And if you plot our number over time, you see it's exponential. Yeah, we've been doing this for 7 years. If it was linear, it would have taken centuries to get to the 20,000, but we're actually accelerating, luckily. One of the other things is we're doing this with the local institutes. We're very aware that for meteorological data, there's local laws you need to oblige to. You can't just barge in, install a sensor network without taking into account that there's a local community already measuring stuff. This is the Director General of the Kenya Met Office with one of the first stations, one of the first new stations installed in Kenya. And we're getting more and more of these pictures with Director Generals from all over the place. And I think we should. We're very happy with that. This data is becoming available slowly. If you go to tammo.org, you can find some on it. So the way we did that was by showing that these local sensors can be made, and also that there is a market for it. But in all these projects, what I every single time ran into, the floaters in Myanmar, the work with my students, and even in Tammo, the first idea for the sensor is not the hard part. And I think we've seen that in a lot of talks today already. Most of the details were then on what we're gonna, Raspberry Pi and uploading and stuff. It's always the data that's the problem we run into. The sensor itself, we understand the physics. So that idea is usually pretty easily done and also easily tested in your own lab or whatever. But getting it to work in the field is usually a pain. And that's what I want to talk about today a little bit, because I have a few ideas about how we can deal with that. And the main thing about that is speeding up innovation. If you want to make it policy relevant and get funding from proposals, you probably should call it accelerating innovations across scales. Bear with me. This is the framework I like to use when talking with, most of you will recognize it when talking with my students about what a sensor system is. This doesn't cover all sensor systems, but it's nice to have as some kind of framework. Basically, we have an outside world, something that is an analog sensor that turns the outside world into an electrical signal. Then that signal is somehow made digital, and if it's just a voltage, you usually have an analog digital converter. If it's something that does pulses, like a tipping bucket rain gauge, it's a timer or a counter. That then is just ones and zeros, so that needs interpretation, and the interpretation turns this digital signal into a digital representation of what we had in the real world. Millimeters of rain, degrees Celsius, degrees Kelvin. That then needs to be like stored for us to collect at some point and or send out online. Sometimes we switch this around. Sometimes we take the raw data, then first store and send it and do the interpretation online. In general, nice framework to work with. The most basic example I always use for my students, and it's also relevant in hydrology, in meteorology, if we go out and do field work, we have a tipping bucket and a logger. And within this framework, that would mean that we have an analog sensor, timer, interpreter, storage to be exactly the tipping bucket is just the analog sensor, and the storage is the rest. The logger is the rest. One of my problems with this is what's the price of a hobo logger? Anyone? $200. $200? Any other guesses? You're pretty accurate, but it depends on who you are. Because if you look on their website, all you get is ask quote, which usually means that they're going to gauge who you are and what your budget is, and that's going to determine what you pay. And if you're not spending your own money, that usually means you don't care and you'll pay it anyway. And most of us are in some way on tax money. If you're at the Met Office or if you're academia, it's not your own money. You're not going to have less to eat at the end of the month. So you're not going to haggle as much as if it was your own money. That's why these things are so expensive. And also that's why it's a very lucrative business to make them. I want to change that, of course. I don't want to disrupt it completely. I'll get back to that. But for sensor development, I want to, There's 3 ways you can look at my framework. And that's 3 roles we have in using sensors. And the first role is sensor development. And in sensor development, I'm really thinking about, I want to make a new sensor. Something that measures something that hasn't been measured before, or measures a variable we're measuring in a completely different way. I want to work on this part. And what I then want is to have this to just work. This was made for Americans. Maybe I should have said bloody or something for the UK. From that point on, anything after this analog interface, I don't want to think about it. And especially if I work with my students, they're civil engineers. They're not computer scientists. They don't know Linux. They shouldn't know Linux. They know water and a little bit of physics. So I want a solution that does that for them. An example of this would be like PT100 analog sensors. If you want to use that in your field, suddenly you need to buy something that does that. Another thing you could do as an academic researcher is not develop your own sensor, but take a sensor from another field and use it in your field. And we've seen that a lot lately. So for example, I call that sensor import. And then you want this entire chain. If I'm importing, for example, the Kinect, does anyone not know what the Kinect is? You don't know what the Kinect is? So I'm assuming the rest does, but just for the 2 of you, this is not fair. Who knows what the Kinect is? This doesn't add up to 100%. Yes. The Kinect is a 3D scanner you put in your living room, and it comes with the Xbox game console. Yes, you could also use it under some circumstances to scan as kind of a low-cost LiDAR soil types. But I don't want to deal with the time of flight sensor-like stuff that's in there on the analog side. I just want to get the 3D scan out. So if you're taking an existing sensor from another field, you want to have access to that. You usually don't, by the way. Demand that if you're dealing with people selling sensors. And there's a lot of companies that understand that. Because you just want to work. One of the examples is what's happening in the maker community. You can buy accelerometers on a chip. And then they're analog, and you have to do the analog to digital conversion yourself. And you can optimize it. And if you're really good at that, you totally should, because it's then more optimized for your project on birds than it is in general. But if you just want to see, can we use an accelerometer to measure something new in another field, demand that it has digital outputs. So it just gives you the G's out, not some in-between format. And finally, if all you do is field work, if you just, please come in, use the students, come in, student. If all you do is field work, all you care about is, I want to have rainfall data because I need it to do an analysis. You just want the entire chain to work. You just want to buy it. You don't want to be bothered with anything else. This is the example of this, and it's perfectly okay if you spend $200 on a logger for that. Because as some of the speakers already said, the amount of headache and hours you need to put in to make something work is sometimes better spent on doing the actual science. If it's just buying something that already exists. I mean, and I'd love for people to make their own sensors, but don't overdo it. Let it, leave the niche to me. That would also be good for my career. Okay, then back to like I said, back to my career, sensor development. What I realized recently in this framework, we can make another distinction when you're working on new sensors. Because the middle part is sensor dependent. It depends on what you're sensing. But storing and sending data should be standardized. So we should have a boundary there, and we should think about that. Because there's a lot of devices out there that already do that for us. And I don't think we should reinvent the wheel. One of the Raspberry Pis come to mind, but one of the devices that came to mind for me, phones. Especially if you want to put stuff online, we can do all the stuff with Iridium, satellite communication, or making your own GSM modems. Everyone has a phone nowadays. It already does that for you. Let's just use that. Which brings us to the middle part. Can we use something standard here as well? And this is especially for my students. Can we just have something standard that is adjustable, so we can adjust it to whatever sensor we're having? And the first thing that comes to mind for me usually is the Arduino and Arduino-like platforms, little programmable boards that connect to the outside world. Has one drawback: you're programming it in C. It's not something that my civil engineering students are used to. Also, connecting an Arduino to your phone, also not really easy. Mainly because your phone doesn't have any entry points. And then I at some point realized, wait, your phone does have entry points, you just can't see them. Because all phones nowadays are constantly scanning for Bluetooth. So what if instead of an Arduino we use something like a Wi-Fi, like a Bluetooth enabled board, and all the board does is it gets some data from the sensor you're developing, and it shouts that data over Bluetooth, blindly. Then all we need on the phone side is an app that listens to Bluetooth, and if it hears anything, all it needs to do is store it and send it up. And that's exactly what we built. I had a student in our informatics, or in our computer science lab, make an app for Android. The only thing the app does is it continuously scans Bluetooth. It has an internal list of MAC addresses, because otherwise it would be picking up everybody's headphones and whatnot. That list of MAC addresses is on a website, and where it lives is just something you can type in on the app as a setting. So if I have another sensor, a new one that I deploy, I just add that MAC address to the list of MAC addresses. As soon as it hears something from a device that's on its list, it just collects it, and then once every 10 seconds it uploads everything to whatever you want. And the endpoint where you send it to, again, is just something you enter as a setting. Which means that for my students, all they now need to do is make this sensor. And as soon as they connect it to this device, it will start showing up online. Let me demo what that looks like. I flew in this morning from Schiphol Airport. Sir, what are you bringing in your luggage? I could understand though. But what I am bringing, this is just a potentiometer, like a variable resistor that I can turn, and then I can measure the voltage over that on the board. So it just mimics any analog sensor. I'll put it in a power bank to show you that it's really not connected to anything else. Then I'll have the app right here. we need a lot of updates and waiting for. So it just has 3 buttons. So you can enter an endpoint. The endpoint is now a PHP file on my website, which I will show you in a moment. I can enter the online address where the MAC addresses live. And it just has a start scan button, which I will just now do. Start scanning. This takes about 10 seconds. It will show me the first measurement as soon as it's there. Yes, 1904 is the first one. Let me just turn it all the way down so it should go to 0. 0. And I'll turn it somewhat up again. You can watch the values. So you see MAC address and value. It will pop up on your screen. I will go to the interwebs. So, and what where am I? Oh, there. Nice. Okay, what I've done now, so this is the PHP file, receive raw data. And from the PHP file, I can forward it to any service that accepts data. I mean, I could put it into a quasi-HIS nice system. If the Met Office had a system where I could upload citizen science measurements, I could forward it there. But for now, for this demo, all it does is it upends it to a file, raw data.txt, which lives in the same directory. You don't see it because I deleted it just before we started. So if I reload this folder, there it is, raw data. So we started with 1904 and then 0, 1162, and if I now start turning on this one, just crank it all the way up, should go something to 2500, I guess. Takes about 10 seconds, 11:55. 2500, there we go. So any analog measurement automatically comes online. So we've automated, if I go back to my presentation, here we are, demo, the demo worked. You know demo effects. So we've automated this part with an app that anyone can use. We've automated this part with a Wi-Fi shield that anyone can program. It's called Wi-Fi, and this comes back to education, because you program it in Python. Most people in meteorology and all people in civil engineering nowadays get taught Python as a main programming language, which for us is so much easier. You don't want to get into all the pointers, registers that C forces you into. Which is, if you want to optimize things to be really low power and very optimized, sometimes necessary, because C lives very close to the hardware. But meteorologists don't live close to the hardware. Write something in Python. And then if you have a working prototype, hand it over to a company and say, optimize this. Demo. But then what will we use this for? One of the things I've noticed is that my students, once they've made a project, it usually ends there. It's been a nice educational project, but there have been good ideas where I thought, what if we could test this for a while next to our KNMI setup? We've got 42 automated weather stations, so we can compare it to the gold standard in the Netherlands and see if this device that a student made is actually any good. You don't get access to these sites. And I get that. These sites are part of an operational network. They provide services that are essential for a lot of businesses, for all of society. You don't want my students, especially not with the kind of attitude I have towards hardware, you don't want them running around your operational site. What you do want is them running around next to your operational site. So we now made a deal with KNMI, and we're starting to do this, where with their sites, you can see this is their official WMO station, which is really next to their building, and they also have 42 sites that are not first level. You have those tiers in the WMO, so I think this is second tier. Those are the 42 stations. You don't want it there. You want it where those guys are playing football. So what we do is we just hook up one of these phones. We agreed with KNMI that would be something we could do. We just hook it up to the power that they do have the phone running continuously, If a student has a new device, it has to make sure that the device runs on its own, solar panel, battery, whatever. But once you bring it within Bluetooth range, and once you add the MAC address of your device to my online list, your measurements are coming in, and you can automatically compare it to that gold standard. So in that way, we can accelerate the innovation in new sensor design. Because usually it takes a lot of talking and going through committees before you get to do like a dual comparison campaign over multi-years, etc. Let's speed that up. And let's not disturb any of the operational stuff, but let's facilitate that we can work together on that. So that's one application of this. There's another interesting application which harkens to which relates to the disdrometers I started with. At some point we thought, why not turn umbrellas into disdrometers? Our disdrometer started with a little piezo disc. What happens if you just put the piezo disc on an umbrella? Then you buy a very cheap umbrella, Winnie the Pooh in this case. For my first prototype, I just glued a Bluetooth headset to it and had it sent to a phone and just listened in and record the raw audio signal. And if you then look at the raw audio signal, and you, like I said, room acoustics, so I should know something about this. If you then calculate just the sound levels in decibel, you see a very nice relation with rainfall intensity. I know because I tested this. This is my balcony, where I live in a quite crowded old part of Haarlem in the Netherlands. This is how I like to do my field campaigns. This is not a WMO site, as in the be away from other structures and stuff. But this worked. The problem I had with this is that at this point, I submitted an extract to EGU, and this is something that journalists pick up on. So before any of this was published, it was on the BBC site. And I didn't even intend to follow up on it. It was just a fun thing to do for once. But then we got contacted by the GPM people at NASA. They want to have underground validation in urban environments of GPM measurements. Brilliant. So what we now have is a student changing this one for one of these. Because if we just get analog signals integrated to sound levels and send that over Bluetooth, anyone walking with an umbrella and a phone becomes a mobile sensor. Phone already has a GPS location, so all we need to do in the app, which we're now not doing, is add location of phone. And suddenly we have mobile stations that do that. So that's a second application of what we just built. And I think it shows that if we do this as the bottom of the entire innovation cycle, I think we can speed up the time it needs for a novel device to become something that's available for people that are just doing field work. Because now we've been doing TOMO for 7 years. It's been a long, frustrating, but very rewarding road. I wish we had done it in 2 years. And I hope these kind of inventions will help to make the next big project, Twiga is one of these projects we're doing in Delft right now, to make the next big projects cycle faster through innovations. Before I close, if you like this, and I've seen a few people that really should have submitted, if anyone is going to the fall meeting in New Orleans, we have is anyone going? Is my hands up? Oh, you're missing out. I'm sorry, because we have the MacGyver session. It's in hydrology, but it's basically a lot of people coming together that made their own sensors, loggers, etc. I think 10 of our 30 posters are about people making Raspberry Pi based logging sensing systems. You would have loved it. But if you're not coming to New Orleans in December, please come to Vienna in April, I think, this year again, because we have the same session there as well. Abstract submission is open. Because of historical reasons, the session is in hydrology. We always try to co-chair it with atmospheric sciences and be as broad as possible. Atmospheric, soil, cryo, because there is no people doing measurement division. I think there should be, but that's another story. So please submit to that session if you're doing this kind of things, or if you're strapping stuff to birds, and if you're going to Vienna. Finally, concluding, if you think this is really cool, before you start, think about what your position is within our community. Are you doing sensor designing, novel sensors? Be part of this. Are you trying to get sensors from another field into our field? Also be part of it, but realize that you should buy ready-made sensors that give digital output. Are you doing field work? Buy stuff that works. That's how it is. And as a final remark, I really think we should accelerate innovations by standardizing solved problems, because that's what we're doing here. We're using a phone as a solved problem, the Bluetooth shield is a solved problem. Use what's available to accelerate our innovation. Thanks for your attention. Am I over time?
You're fine.
Thanks.
Yeah, Ben.
How much is your microprocessor, and can I have a copy of your app?
I think this thing is $19, but I'm not sure, and yes. Since my student doesn't have a premium account on GitHub, you can just download it. Okay. It's work in progress. But
Any questions?
Are you aware of a company that is trialing, it's like Uber for umbrellas, where you can just pick up an umbrella and rent it around the city? I think there was a trial recently, I can't remember where it was. That'd be a good way to get them always used.
Oh yeah, so
just sitting at home if they won't.
is that a UK-based company then?
I can't remember. I remember reading about it. I have no idea where it was.
Didn't it get pinched? I swear that was a follow-up story.
Yeah.
It sounds really interesting. I'm kind of opposed, but that could be my somewhat leftist academic disposition. I'm somewhat opposed to the Uber of this, Facebook of that system, but I like the idea. I write a column in a popular science magazine back in the Netherlands, and we have, I think I've seen it in London, the bikes you can get, and so we have that from our train stations. If you've ever been to the Netherlands, you've seen like yellow and blue bikes. It's tied to your Oyster card, so it's the same system. You just take a bike. And I wrote a column about we should do this for umbrellas as well. And now that you mention it, if we do that, we should also include this. It's very logical. Good suggestion.
Good questions?
I suppose just a comment from the manufacturers really. As a manufacturer of rain gauges and of data loggers, I think one thing I've been hearing a lot today is not including development costs.
Yes.
And I think that needs to be remembered, that obviously we have to, and that's probably why you get this question mark over give us a quote. Because certainly I run a company of just 8 people, and you have to try and get the investment back, and you know, if you can, I wouldn't call it exploit the big organisations, but if you know you can get maybe a bit more money out of that, you're not exploiting the individual users.
No, I get that.
You see where I'm coming from?
Yeah, I see where you're coming from, and I like that if you do the exploitation side on the Facebooks of this world, and the ones not paying local taxes, but that's another story. It's also a very cheap, no, I shouldn't, anyway. What I think we should really do is we, as a community, recognize the value in having these devices, which is why we are allowed to spend tax money on doing the first level development, which is basically venture capital, I guess, which the state is never getting back. But we're publishing this open source, so if we're done this part, please lower your development cost by starting where we stop, and not reiterating that. Having said that, I'm not a product developer. I will never be one, because that is such a different skill set. The skill set from ID, a lot of duct tape, first proof of concept, is kind of orthogonal to first proof of concept sellable product. Because you don't, if I open one of your products and I find duct tape, you're out of the market. So.
And a lot of products we bring out have had 10 years worth of field testing before somebody even uses it. So you can imagine the costs involved in that.
And that should be something we do way more
Exactly.
on a basis of working together instead of just throwing it over your hedge and then having one waiting 10 years and